Welcome everybody to the ECT Star seminar. This is the first seminar in a series that will be run remotely because of the given circumstances. And hopefully in a few months we will be back running this live. But for now we just run it remotely and record the speaker and will make the seminars available on the webpage of ECT Star for other people to look at. Our speaker today is Kirill Boguslavski, who has been invited by Jarko Peuron, and Jarko is now going to introduce him and moderates the presentation as well as the discussion.
Okay, thanks. So it's our pleasure to have Kirill here today. So Kirill got his PhD in Heidelberg in 2016, and then he was a postdoc in Jyväskylä between 2016 and 19, and now he is an assistant professor in Vienna University of Technology. And today he's going to talk us about non-perturbative properties of gluonic plasmas. So so the time was 45 minutes, and well, okay, I guess. And Kirill preferred to have the questions during the talk. Okay, so Kirill, you have the stage.
So thank you very much for the kind introduction. I'm very, very happy to be here. And I wanted to talk about the non-perturbative properties of evolving gluonic plasmas. So in this topic, I want to discuss mainly quark-gluon plasma in heavy ion collisions. I will, of course, introduce into that and explain what I'm going to talk about exactly. It will not be 34 slides as seen down there. It will be more of about 25 slides, but I will of course also skip a few slides if necessary. The talk is mainly based on a few papers that have been published recently or have been submitted recently. And yes, as has been said before, I wish, of course, if you have any questions, please go ahead and ask them during the seminar. Do you see also my mouse when I show something?
Yes.
Very good. Right. Thank you very much. All right. Okay. So I will start with the motivation, and afterwards I will go on with universal classical attractors. So this will be this is a topic that I think covers basically very typical far from equilibrium situations. I will go on discussing spectral functions of pre-equilibrium quark-gluon plasma, and then I will discuss a few interesting properties of the quark-gluon plasma far from equilibrium that have been discussed or found recently. And finally, I will conclude. Now, you find non-equilibrium dynamics in many different systems. So, for instance, in heavy ion collisions, in the early universe, and also for ultra cold atoms. And there are very different systems underlying them. So, longitudinally expanding non-Abelian plasmas, relativistic scalar systems, or non-relativistic scalar systems, which are basically Gross-Pitayevsky equations. But what is interesting is that when you look at the regime where your coupling constant is small, so much smaller than 1, and you discuss closed systems, and with the property of having high occupancies, we'll discuss when you achieve that, then you can actually describe those systems in a dual way and with different methods, basically non-perturbatively using classical statistical simulations, and kinetic theory, or more generally, some perturbative methods can be used as long as occupation numbers are not too large. And this way, you can basically you can study with lattice methods, with non-perturbative lattice methods, what is going on far from equilibrium, while trying to understand what's going on with kinetic theory or perturbation theory. And then you can also, of course, see properties that are not very well described by kinetic theory or perturbation theory, and this basically tells you what genuinely non-perturbative phenomena are. We will be discussing heavy ion collisions. So we will be discussing heavy ion collisions where we have, well, basically the main facilities are the LHC at CERN, which is also shown on the right. I hope it's also visible, and the relativistic heavy ion collider, so RIG, which is at BNL in the US. And some of the main observables of those huge facilities are to understand and to study quantum chromodynamics at high energies. And one of the states which are particularly interesting is the quark-gluon plasma state, which is also thought to have existed in the early universe, which is also why it is so important to understand. Now, right after a collision of two heavy nuclei, this pre-equilibrium system, this quark-gluon plasma, is created between those nuclei. So while so after the collision, while they fly away from each other, this quark-gluon plasma actually evolves. It consists, as it's called, of quarks and gluons, and basically forming at first some pre-equilibrium matter medium, and afterwards it becomes basically a fluid, and then you have the whole machinery of viscous hydrodynamics and then other steps and other stages of its evolution. What we will be considering is only the pre-equilibrium dynamics stage. And the question that we will be asking is, how does actually the quark-gluon plasma, the pre-equilibrium quark-gluon plasma, evolve, and what are its properties? For that, what we will be using is, we will be assuming the limit of high energies, which means that we will be only considering weak couplings. And initially, there will be also, so in this limit, what you have is, you have huge gauge fields, where your gauge field is of the order of the inverse coupling. So if the coupling is small, this means that the gauge fields are as large as they can get, basically. And similarly, you can also define occupation number, which will be defined on the next slide, and also the occupation numbers of gluons is basically 1 over the coupling, which is very, very large. Just as a reminder, classical equations of motion of non-Abelian gauge theories. So we will be discussing basically non-Abelian gauge theories, since gauge fields dominate the dynamics initially because of their huge occupation numbers. Now, when you have a situation where your occupation numbers are very large, as already said before, lattice methods become available. And with lattice methods, I actually mean classical statistical lattice methods. So what you do in there is, first of all, you discretize your space. And what you do is you select some initial time, which you call T0. You choose some quantum Gaussian initial conditions, or some initial conditions, by choosing the variances or the correlation functions of AA or EE correlators, and which formally define some weight functional for the initial time, and you solve your classical equations of motion for the dynamics, for E and A. And with this, so you do that for different configurations, and after evolving them until some time, you can actually define or extract your values of your observables at that time by only averaging them over the different configurations. Those configurations, since you only initialize correlation functions, this means that there is a lot of degrees of freedom that you can average on, because only the correlation functions are well defined, or are defined at early times. At the initial time, sorry. And we will be discussing a lot about distribution functions. And a distribution function, which I also called slides before occupation numbers, is basically given by such a correlation function of EE fields. Now, this T just means transversely polarized, and the omega of TEP means just the dispersion relation of your gluonic fields if you have gluonic degrees of freedom. And basically, for large momenta, omega is basically P, just your momentum. Right. Now, what happens if you start with such a highly occupied system? Now, and this is not only a scenario from those classical statistical simulations or just from kinetic theory. This is basically by doing different methods, you see that these classical attractors emerge in your system. And so what you find is, with such an overoccupation, highly occupied initial condition, the system basically, at first it approaches an attractor state, a classical attractor state. So before thermal equilibrium, it approaches what can be called non-thermal fixed point, or more generally a classical attractor. And at this system, or at this state, what you find is you find some universal behavior. So first of all, the exact initial conditions, so the form of your distribution function or the values of your fields and so on, they are lost basically. And what you find instead is you find a distribution function which evolves in a self-similar way. And self-similarity means here that you can, while it was initially a function of time and momentum separately, you can actually scale out your time dependence, and then you get only a scaling function of a single argument, of a single variable. Now, such systems where you have this kind of distribution function behaving in such a way have been observed already in also experimentally with ultra-cold atoms, and they have been basically predicted already a couple years ago in different works. And also what is interesting is that you can also summarize them into universality classes far from equilibrium. So you can classify the dynamics in terms of universality classes, and there have been also some predictions on that. Now, our first example for that is a direct energy cascade. So we will be discussing now an isotropic gauge theory. And for the gauge theory, what you find is, so you just let it evolve, the system, and at some point you see that you get some universal form. So the universal form actually consists of a power law, basically P to the minus K, and then some very quickly decreasing functional form. And when you evolve it as a function of time, so basically this dashed curve becomes the black curve at a later time. So what happens is that this typical momentum where the energy density sits, because the energy density is basically given by P to the power of 3 times F, and the energy and the integral over that, and those momenta here dominate the energy density. So energy density basically evolves to higher momenta, and this is what drives the thermalization process of such systems. We can call this hard scale, this hard momentum, a hard scale, and for this system it evolves as a power of T to the power of 1/7. And those exponents are universal that are in this kind of system. We can also find a soft scale, which I will introduce a little bit later mathematically, and this evolves to lower time. So you also find some kind of scale separation. Now let's go to actual heavy ion collisions. Now, shortly after the collision, what you find is that your system, so if you start with a highly occupied system and you introduce a Bjorken metric in your description of your heavy ion collision, then you find that the distribution function of the system approaches again a self-similar state, which is, now we have to distinguish between the transverse momentum, basically the transverse momentum with respect to the collision axis, and the PZ momentum, the longitudinal momentum, which is in the direction of the collision axis. And what you find is that this distribution, which is a function of 3 variables, becomes a function of only 2 variables times some power law in front of that. And those exponents, alpha, beta, and gamma, are also universal. So you can start with different initial conditions, and you always end up with, or most of the time you end up with those kind of exponents. So let's have a look at the distribution function itself. So when we think about how does it look like for some fixed pz equals 0, which is basically looking at in the direction of so for different transverse momenta, what you find is you find a very similar form as here. However, you have no evolution to higher momenta, and you just have a drop of your occupation numbers. And when you look at the longitudinal profile in the pz direction at some fixed momentum, transverse momentum, you find that it shrinks. So the amplitude becomes smaller, the pz direction becomes smaller. However, you can rescale the amplitude and the pz direction, and you get something which is universal. And this is exactly what is meant by this Fs. You can also rescale the transverse distribution. Now, why only do that for gauge theories? We can also just use scalar field theory for comparison. And this is something we have also done. What we found is that for scalar lambda phi to the 4th theories with ON symmetry, basically, we found that you get to exactly the same self-similar attractor. So the same scaling function, same alpha, beta, gamma, all of that are the same. And you see that also here in this plot, where you see for different times the scalar contribution rescaled with appropriate alpha, beta, and gamma. They all collapse to a single curve. And the same curve is also the gauge theory curve. So the same the same scaling function is valid for gauge theories and scalars. And this is something we coined, or we conjecture to be a universality far from equilibrium. But apart from this universality statement, what is also very important for such classical attractors is that they can be used to distinguish what kind of connected description are underlying the dynamics. And this is so with this we actually use those simulations that I showed you here, and those alpha, beta, gamma we used in order to distinguish between different kinetic theories that were proposed in the literature at that time. So there were some which also included some plasma instabilities, some condensate, and so on, which were very specific theories. And what we found was that all of that does not matter, and the main thing are just elastic and inelastic scatterings. So basically, we found that this classical attractor is consistent with the first stage of the so-called BMSS scenario, and with that, this helped to establish that the effective kinetic theory is indeed all you need in order to describe the dynamics also far from equilibrium. And this is now, I mean, this has been known before. This kinetic theory has been known before. It's basically the typical left-hand side of the kinetic theory, and then elastic processes and inelastic processes. But now it's also used as a standard description when you think about your description of your quark-gluon plasma from a weak coupling perspective. Now we have seen that those classical attractors are interesting because we can also say something about kinetic theories, but in order to say something about kinetic theories, we should actually have quasi-particles, degrees of freedom. So we should actually show that quasi-particles are the dominating excitations or gluonic quasi-particles are the dominating excitations in your system. And in order to understand what actually are the excitations there, when is kinetic theory valid, what is very useful is to know something about the spectral function. So the spectral function of QCD, and also of other theories, if you think about other situations, physical situations. And the question is, what are those out of equilibrium? Now, in order to do that, one can also use perturbative frameworks. For example, Hart loop or Hart thermal loop framework, which can be used if you have a scale separation. So in the Hart thermal loop framework, what you can do is you can define your soft mass scale. You can divide that by your temperature scale, which gives you basically your coupling constant. And if this is small, this is your expansion parameter that works very well. In our case, what we need a ratio between the mass and the hard scale, because the temperature is, in our case, out of equilibrium in the hard scale. And this works for many systems, as we have already seen. We have seen an example for this system with the isotropic gluonic plasma. So we can use hard thermal loop theory. However, it's still important to know non-perturbatively how the spectral function is. And in order to do so, we have developed a method for that, where we combine classical statistical SUN simulations with linear response theory, and we use a very important we use linearized equations of motion that have been developed here, and so this framework actually is consistent with Gauss law separation. All the important consistency conservation laws are respected by that. And what we do is we basically take our classical fields, we perturb them with some wave, for instance, and we follow this perturbation itself, or the response to this perturbation, and the response actually gives us the retarded propagator, and the retarded propagator is connected to the spectral function. This is the way how one can compute that, and we apply that here to the self-similar 3+1 dimensional gauge theory state that we already discussed above, because here we have actually a scale separation of the mass and the hard scale, at least at later times. Now we did that, and our results are basically shown here for the transverse spectral function, here for SU2 theory. The spectral function is basically a commutation correlator of A fields, and we look only at the transverse degrees of freedom here, but we have also looked at longitudinal ones. And on the left-hand side, you see it as a function of delta t. So once again, you get a response in t minus t prime, but then you can Fourier transform with respect to delta t, and then you get the frequency space. So on the left-hand side, you have delta t space. On the right-hand side, you have frequency space. But in the frequency space, you can actually interpret the results. So you see a large excitation, and we have also shown that this is actually, at least we have shown it for larger momenta, that this is of Lorentzian peak, and so you actually have quasi-particles here. And you also see this very interesting structure for low frequency, so for frequencies up to the momentum scale. And this structure is the Landau damping structure, which is a very specific form, has a very specific form, and you can actually compute it analytically, which has been done using hard thermal loop theory. We have even just used the leading order result, because the next leading order result has been only done for thermal field theory, and only very recently after this work has come out. And so you see that our basically full non-perturbative result is consistent with this perturbative prediction. But what we also see...
A question here. I'm familiar with Landau damping in fermionic systems, you know, where you have a Fermi sphere or something like that. But what does Landau damping mean for a bosonic theory?
Right. This basically tells you that yeah, I'm sorry, I'm mixing up all the time the terms, that I didn't want to say anything wrong there. But I think the basic picture is that you have some particles at frequencies below your momentum. And the reason for that is that you're at some that you have different directions with respect to your wave. So basically, you get quasi-particles. Depending on the angle, you get a different quasi-particle energy, and this gives you a continuum. I think it is in this sense a bit similar to fermions, but this was a very crude explanation. I can tell you mathematically what it is. It's simply when you think about yourself, about your one loop self energy of your when you think about your self energy of your gluons, of your gluonic fields. And then what you find is that you get a cut. You get basically logarithmic expressions in there, and when you take the imaginary part of that, basically going from the retard propagator to the spectral function, you find a cut of your logarithm basically, and this gives you again a continuum which only survives for momenta, for frequencies up to momentum. I must apologize that I did not give you a proper explanation for that, but at least mathematically.
Thanks.
Okay, but another interesting thing that we found here, what we saw, what was of course expected, is that your quasi-particles do have a finite width. The finite width means that they have some lifetime. And when you think about Hartman loop theory at leading order, those lifetimes, well, this is a next leading order effect. That's why at leading order they have not been predicted. Well, at least not for all momenta. But let's go on. Let's first discuss for a moment the dispersion relation of those quasi-particles. So I will not talk about the Landau damping or Landau cut here anymore. I will be mostly talking about the quasi-particle excitation. Now, the place where you have the excitation actually gives you the dispersion relation. This is your omega of p, and this is shown here for transverse polarized gluons and for longitudinal polarized gluons, and the predictions are shown in red. So except for very low momenta, you have actually a very nice, mostly qualitative, but very nice consistency between the perturbative results and what we found on the lattice. But when we went to gamma, to the damping rate, to this finite width of your excitations, we found, well, we were able to extract the full momentum dependence of that. And what is interesting is that at very low momenta, up to the momentum scale, you have actually you observe that both the longitudinal and the transverse gluons have the same width, also, although they have different dispersion relations. So this was one observation. Now, what was the perturbative prediction? The perturbative prediction was basically only p equals 0 and p equal infinity. And but for p equals infinity, what you need is estimate of your magnetic scale. But for our system, basically the estimate is very crude. So basically you get error bars which also include our large p value, but they are basically like that. That's why it's not written here. For p equals 0, you get a value here, which is very close. It's qualitatively very close to what we find. It's a bit overestimating our non-perturbative result, but it's still in the same ballpark. But this was the first time that one was able to actually extract or to get the damping rate of within for your gluonic excitations. And we also argued that this should be similar or maybe even the same in thermal system, because what we used here were essentially thermal the thermal Hartman loop results, just using for their parameters, just using our distribution function that we were able, for instance, to hide in some parameters like the mass or effective temperature and so on. Okay, now we have now discussed what kind of excitations you have in the in your isotropic gluonic plasma. But the question is now, what about the kinetic theory at extreme anisotropy? So what happens if you have a gluonic plasma which is completely anisotropic? Anisotropic means here in momentum space. So when you have a large transverse momentum extension, but basically you have only pz equals 0. And this situation mainly, well, when you think back here to this a situation where we discussed heavy-ion collision and the classical attractor, there we had a very anisotropic distribution. And when you go even further, when you go to extreme anisotropy, you basically end up with such a 2+1 dimensional plasma effectively. The question was, what do we observe? And we found basically again a classical attractor, and this and we were able to understand its dynamics in terms of kinetic description. So it was not a complete kinetic framework, because the problem with 2+1 dimensional systems is that Hartema loop already breaks down at the soft scale. So you already have to resum an infinite number of diagrams. You basically have to reorganize your perturbation theory already at your soft scale, which is at the moment, as far as I understand, not possible yet. However, we were using kinetic arguments, and we were basically qualitative kinetic arguments, not complete quantitative ones, and these were consistent with our observed exponents. So, which actually meant, since we were able to use some kind of kinetic arguments, this actually meant that probably quasi-particles do exist. And this is now a work in preparation. So we then thought, well, let's try to look at the spectral function, the full spectral function also of 2+1 dimensional systems. And you find that in 2+1 dimensional systems, you also see maybe very, very, so this is the frequency and space, and this is the momentum space. And so far we have only looked at the spectral function at some fixed momentum, but now you see also the full frequency space. So this basically gives you the dispersion relation of your quasi-particles. You see that although the width of those quasi-particles is very huge, very large, as compared to your 3+1 dimensional system, you still see some sort of quasi-particles. At large momenta you see them directly. At low momenta there is something interesting going on at very low frequencies, which is beyond just Landau damping, but you can still see that there are some dominating quasi-particle-like excitations. Now, when you think about the longitudinal degrees of freedom, you again see, so this is now the omega equals p line, and Landau damping you get for frequencies below the momentum. And this is exactly what you see. So you see something below, so for frequencies below momentum, and you see that also for 2+1 dimensional systems. So in this sense, qualitatively, it works very well. It is what is expected in perturbative treatments. However, there are interesting differences that we will be discussing later on, but I can already basically tell you that the difference is, well, some differences is this huge the huge width, and there is some Gaussian profile, and there are very large actual quantitative differences from what you would expect naively from Hartema loop theory. We are also working on spectral functions of fermions at the moment. So far what we have done is we have thought about heavy ion collisions. We have thought of what are actually the underlying degrees of freedom in heavy ion collisions, and we have found that, well, quasi-particles are describing them very well, and even for large anisotropies, you see Landau damping, you see all those different important features, what you would expect. Now, why not use that also for other systems? And what we did is we used also scalar field, so we extracted the spectral function in a scalar field theory far from equilibrium. Now here the difference is, here the motivation is a bit different from what we had before. Here we have the following problem. We have again a self-similar regime with different exponents alpha and beta than what we are used to, for instance, in gauge theories. And we now look only at momenta which are very small. So we only look at momenta below the mass scale, basically. And there we see that the distribution functions are much larger than 1 over the coupling. So you get a huge occupation number. And what is even more disturbing and more surprising, is that you get the same form, the same exponents for all n, even for n equal 1, n equal 2, n equal 3, etc. So for large n argument, for large n theories, you could actually expect, well, okay, you resum, you do basically 1 over n expansion, and then it works, and it indeed works. But why should it work also for n equals 1, n equals 2, for very small n? And this has been, this was for quite some time, this was a question, and only with basically spectral functions and other other unequal time correlators, we were able to understand what is actually happening in the system. And what we found is that this huge universality class consists actually of 2 universality classes, so it splits actually. So for n equals 1 and n equals 2, what you find is that you find some non-Lorentzian peak, which is basically not really a quasi-particle peak. We think it is connected to topology or to vortices. It has very different properties than for larger n, and for larger n, starting from n equals 3, we see that you have really nice peak that you would expect from large n excitations, that you would expect from your perturbation theory in a 1 over n expansion. So you have a splitting in those different n theories. You see that also in spectral functions there is a huge difference, and this is basically a first step into a classification of your classical attractors, of your non-thermal fixed points. So basically a classification of universality classes. And this is something I would also like to go on in the future. And I think this is a very interesting and very rich topic, because so far people have not looked too much into this far from equilibrium situation of closed systems. Now, let's go back to gluonic systems. Now, transport coefficients are very important in order to keep in touch, to have some connection to actual phenomenological observations. One of those interesting coefficients is the heavy-quark diffusion coefficient, because it tells you, so it gets into the description of how a heavy quark actually evolves in a quark-gluon plasma, or how quarkonium evolves in a quark-gluon plasma. Now, quark-gluon plasma, as we discussed, is not only a thermal system, and so far these kind of dynamics were mostly discussed in thermal systems, but it also has a large pre-equilibrium phase. And so what you can imagine is you have basically a heavy quark or quarkonium, and you get kicks from the matter, from the medium around it, and this medium is the quark-gluon plasma. In this case, it's a pre-equilibrium quark-gluon plasma. Now, what is interesting is that due to those kicks, you get, of course, some momentum broadening. Well, the kicks are not actual kicks, but of course, it's more of a chromoelectric force or some QCD interaction, which amounts for very heavy quarks into a basically chromoelectric force. And you can describe its momentum broadening, p squared, in terms of a gauge invariant observable. And this is basically given by an EE correlator in a gauge invariant way. And this is something you can compute on your classical lattice, for instance. So again, we come back to our description where basically of this isotropic gluonic state that we have already used before, because here we can use classical simulations and we can also compare to perturbation theory in order to learn something about non-equilibrium and non-perturbative effects in this evolution. So what we observe here is the p squared as a function of time. So you find a very quick rise at early times, and then you see those oscillations, and this is basically diffusion, what is understood as diffusion. So you see a rapid initial growth, which we understand its functional form. It's basically due to decoherence of your fields. Then you see those damped oscillations, which we will be discussing in a moment, and then you see the overall approximately linear growth with time, which is what is also expected in a sense of some Fokker-Planck-like equations. Now, So far this is p squared, but when we take a time derivative of that, this is actually something that we can consider. This is actually the heavy quark diffusion coefficient that is known as a transport coefficient. Now, far from equilibrium, what we see is after this very huge initial evolution here, very quick initial evolution, you see those oscillations, and those oscillations actually go with the plasma frequency. Now, when you don't rescale time and the heavy quark or this EE correlator kappa, then what you find is you find different functional forms. This is very similar to what we saw before with the classical attractors, where we had different self-similar or different forms, and then we have to rescale its variables, basically its amplitude and its variables, and then we got something universal. And this is exactly what we observe also here for this functional form. So what we rescale it with is the heavy quark diffusion coefficient, which is basically defined as the large delta T limit, or basically the offset of those oscillations, well, with plasma frequency. And you see that all of those different curves basically fall on top of each other, which tells you that there is something self-similar going on. Now, before going into those oscillations, where they come from, let me say just a word about the heavy quark diffusion coefficient itself. It, as a function of time, it decreases with time. However, when you think about that it decreases and at some point your system thermalizes, it stops decreasing basically at some point, and then it hits the thermal state. The thermal state, it also hits the thermal value. So what you find is that at early times your heavy quark diffusion coefficient is actually much larger than your thermal value. And basically similar observations you can also do with other transport coefficients. So usually people model something before actually the quark-gluon plasma hits its thermal-like state, the hydrodynamic state. In order to, for instance, to describe heavy quark diffusion or jet quenching, but we argue that the far from the out of equilibrium dynamics is important. Is actually also very important for the dynamics of this heavy quark diffusion, for the heavy quarks or quarkonia, or for jets basically. What we also, I told you a couple of times that we need to also compare it to some perturbative dynamics, and the perturbative ones are the spectral reconstruction, which is this SR curve here, where we basically use our spectral function or basically the spectral function for high thermal loop theory, basically with some extensions that I will be talking about in a moment, and we use that in analytical computations. And this is basically a more or less perturbative prediction. And the real perturbative prediction is using kinetic theory, where we use known expressions which are analytically computed. And this basically a bit underestimates. So basically this treatment overestimates a little bit, and the other one underestimates a little bit what we actually see for the heavy quark diffusion coefficient. Now, what is interesting and important, and maybe one of the reasons why those treatments don't work perfectly, is that what we actually find on the lattice in our non-perturbative classical simulations, we find that the EE correlator at equal times, which is basically your distribution function, it actually overshoots what would be expected from a hot thermal or from a perturbative expectation. Even a non-thermal expectation would actually say that you should not have this excess of infrared gluons. But this is exactly what we find. We find it also in 2+1 dimensional systems, at least for the scalar component there. And we also, and the question is, well, this is a gauge fixed quantity. Do you actually see that also in a gauge invariant observable? This is not having a condensate, but it is still an excess of gluons that you should account for when you think, when you discuss transport coefficients or other observables. And the reason why one should actually account for that is that there is a huge difference if one does not. So for that, we look again at the coefficient, well, here as a function of delta t. Basically, this correlator, which is the time derivative of p squared. We look at it with those different methods. So the spectral construction method and the kinetic theory method. And you see, so the lattice data, it shows what we already saw. It shows those oscillations. Now, when we do the spectral construction method, which is using the full spectral function, you actually see that you also have described correctly those oscillations. Well, this offset is a little bit is connected to the offset that you see also here when comparing data and spectral construction. Now, when you use a form without this infrared enhancement, so basically when you construct this form, and you put into the analytical computation, then you find this green curve, which barely sees any oscillations. So those oscillations are a very clear sign of having excess of gluons, especially if the oscillations go with the plasma frequency. Now let's discuss the kinetic theory framework. So for the kinetic theory framework, we have not used the full kinetic theory, but we have simplified it a little bit, probably with this killing the oscillations. But what you see is that when you, again, when you discard any infrared enhancement, which is the lower curve, then it's a huge difference. So basically this is our kappa, our heavy quark diffusion coefficient, which we showed here. But if we discard of this infrared enhancement, then it's basically half of its value. So it's a huge effect on kinetic theory, on perturbative effects. And the last question about this here is what is actually the origin of those oscillations? We can split basically our heavy quark diffusion coefficient into different parts, because we can split also those different parts in our spectral function as we discussed. So we have Landau damping parts, we have quasi-particle parts, and what you find is that the quasi-particle parts are actually the ones important for these oscillations. All right, now this basically reveals, so these infrared dynamics could be also found in other contexts like jet quenching, quarkonia, and they may be, and they would be then connected to genuine non-equilibrium quark-gluon plasma physics. Now the last two slides, and then I'm really done. I hope I'm still in time somehow. So the last two slides, and I will be tried to be very quick, is that we thought one thing is to see the infrared enhancement and to see something in gauge invariant, negation invariant quantity to basically see that effect. But a completely different one is to say what would be actually condensate in gauge theory. Now, a usual condensate would actually mean to have gluons which are occupied in a very, very small momentum regime of p equals 0. But this is from kinetic theory or from perturbative arguments, this is not possible. However, the question is, maybe there is a different notion of what one could define as a gauge, as a condensate, and which would be also gauge invariant. What we use to that, and this is not having large number of gluons, this is connected to something else, to some conservation law. And so what we used for that are Wilson loops with a very, very large extent in one direction, where c is approximately 1/2 or 1/4 or whatever. So basically you're talking about very large, very long Wilson loops, and the delta x direction is variable. And we define the condensate fraction as basically a volume integral over the expectation value of those Wilson loops. The original one for different volumes, well, you see that there are very different dynamics. However, when you rescale time by something that can be called condensation time, then you find that all of those curves become universal, so they drop on the same curve, and this is basically given, the evolution of that is given with a universal exponent zeta, which is given by that. Now, this condensation time, or the condensate formation time, it is a function of your extent of the volume extent. And the volume extent, well, basically, a reasonable definition of your, or a reasonable understanding of your condensate is that it should also, the time when the condensate is being formed should actually increase with volume. And this is exactly what you see here, because the value here is positive. And so, okay, this is, at the moment, it looks like, well, it's a peculiarity, yes. It seems to have properties of a condensate, which could be, or properties that could be defining properties of a condensate far from equilibrium, but what is it connected to with, well, what is the physical interpretation of that? And for that, we can compare to scalar field theory, where you have an interpretation of the excitations. So there, what you use as a condensate are actual quasiparticles. So you define a quasiparticle excitations in a very similar way as what you do here. And you see the same phenomenon. You see some growth which starts lower the larger the volume is. And then when you rescale time with a condensate formation time, all of those curves are on top of each other. And the exponent is even similar, but well, this is a different question. But this basically tells you that, well, this is something really one can call condensate. Here we call it gauge-invariant condensate, basically as a comparison to this one. It may, however, have also consequences in your hydrodynamics or other phenomenology, because this is a non-perturbative effect. So perturbation theory would have a hard time describing that, because here we are dealing with length scales which are very, very much larger than the inverse mass. And let me also say one more thing here. If we did not have any dynamics here, but if we, for instance, started with a classical thermal, or with a thermal state for different volumes, then we would not, then basically all of those different curves just would stay stationary, and we would not have this nice increase of this observable. Okay, with that, I'm actually already concluding. So we have discussed pre-equilibrium quark-gluon plasma and heavy ion collisions, especially in heavy ion collisions. We have seen that, or I tried to argue that it is important to have non-perturbative and perturbative methods to compare to each other in order to understand what is actually, what is maybe something which is generally non-perturbative, and how kinetic theory might be extended in order to also get these properties right. Classical attractors are very useful for that, as playing grounds basically. And spectral functions also are important because they reveal basically the underlying dynamics. So when is kinetic theory applicable? They can also be used to classify universal dynamics far from equilibrium. And transport coefficients are also very important because they can be pretty large, and they can also show some non-perturbative properties, and especially far from equilibrium. So especially of the pre-equilibrium quark-gluon plasma, it is important to understand them in a better way. And then we also discuss condensation, engagement, and condensation. Now, as an outlook, what I wish to do is, and I'm also already doing a little bit, also with Jarko, for instance. So I would like to do spectral compute spectral functions also for other systems, for instance, for fermions, expanding systems, and other ones, because you can learn a lot about the underlying dynamics of them. Then different transport coefficients, for instance, jet quenching coefficient, and also heavy-quark diffusion coefficient for other settings is also a very interesting and very fruitful way to understand pre-equilibrium quark-gluon plasma. And also understanding this infrared excess of gluons or gauge-invariant condensation is something I wish to do in the following. And with that, I would like to thank you for your attention.
Okay, so thank you, Kirill, for this interesting talk. So do we have any further questions at this point?
Yeah, okay, maybe I would like to ask a question.
Mm-hmm.
Okay, go ahead.
So Okay, kind of a generic question. I saw that in most of your talk is mostly was described in terms of 2-point functions, like from the beginning, like, you know, with the theory of the universal attractor. I guess you said that everything goes to a universal function, independent of the initial condition, but I guess those initial conditions, they were always kind of a Gaussian, right? Which means that only a 2-point function was characterizing them. I mean, was there any higher point function that you could put there and to see if you still have a universal attractor, or has this been taken care of? And also later on in your talk, somehow you have a system which in principle can be strongly coupled. I understand that in the limit of the kinetic theory for very high momenta, probably what matters is only the occupation number. But when F, let's say, is 1 over alpha, somehow, let's say, higher collidators of occupation numbers should play a role in describing the system, or no? Or they are just quantities that you are not interested in it, let's say. So is the expectation value of F squared equal to the expectation value of F squared? Or it doesn't matter for the quantities that you look at somehow?
Okay, so there are two questions, right? Let's go to the first question. You could also start with an initial state. Let's say we have a classical thermal equilibrium, which is of course a very bad state to start with, because you have UV cutoff problems and so on and so on. But what you can do is you can actually cut off part of that by hand. So basically, you can have your classical thermal system, which has an infinite number of correlation functions, right? And then what you can do is what you can basically put an algorithm on that, basically cutting off parts of your high momenta, and this basically gives you some kind of system of this kind. So you don't need to have only 2-point functions in the beginning or 1-point function. You can also start with 4-point function or whatever you wish. The point is that the 2-point functions are very useful to understand when you can actually trust your simulations. So what I have been doing most of the time was I've shown you mostly 2-point functions, but those 2-point functions were more as an observable, or meant to be more of an observable, and also to understand to what extent you can still trust your results. Now the question about self-similarity is not only for 2-point functions. Yes, I have written this in terms of 2-point functions, but then I have also discussed 2-point functions of unequal times. And what I have not discussed are 4-point functions and other functions, but also those when you are at the self-similar attractor, also they lose their initial basic details of the initial conditions, and they also follow a self-similar evolution. There has been even a paper recently with similar authors as here, where they have computed the full 4-point function in this infrared, in a similar system like that one. They have done it experimentally, and they've seen that also the 4-point function is a function of momentum basically, but it also has it should also be self-similar at the attractor. I'm not sure if they saw that, but they've seen a momentum dependence of the 4-point function, and this is the same momentum dependence that one would expect when we use 1 over n theory, 1 over n expansion, and perturbatively compute in this way the 4-point functions analytically. One would basically one sees that the 4-point function has also some self-similar behavior, and one can also understand its momentum dependent and so on. And I have also basically a paper on that in classical for scalar theories. So it's not only 2-point functions.
Okay, thanks.
Now, what was the last question, maybe, or
no? I think that's it. I think that.
All right.
I think you answered the question. Yes.
Can I ask also a question again? maybe you put up this colorful picture of the classical attractor and the system and the thermal state. My question is, yeah, this one, for instance. So you have a given system, say a given bosonic system. Will it always run through this non-thermal fixed point, or is there the other path, the blue path, also possible? And if no, what does it depend on? You know, you mentioned ultra-cold atomic gases, where you, of course, can play with the coupling strengths, so Feshbach resonances and so on. Go, for instance, into the weak coupling and strong coupling limit. And is it known how these, you know, when this universality fixed point or a non-thermal fixed point is approached, and in which cases it's not?
So I hope I did not say that all initial conditions lead to the non-thermal fixed point. This would be wrong. There is only a set of initial conditions, which I will specify in a moment, that lead to this one. So when you have a large coupling, for instance, then you will definitely not go into this kind of classical attractor. There might be a different attractor, but not a classical one. You might have, for instance, a hydrodynamic attractor, but this is a different question. Now, usual initial conditions, which are not basically insanely overoccupied, or which are already very close to thermal equilibrium by basically only making a small change in your initial condition, they will relax to your thermal equilibrium. You will also not get to this non-thermal fixed point. So you really have to find specific, or to define specific initial conditions in order to find these kind of attractors. Now, in heavy ion collisions, it might be that the energies to get there are not large enough. So although you have probably this kind of initial state, your coupling is still somehow moderate, of the order of 1. So what has been shown in using kinetic theory is that basically you still get to an attractor, and you still get, you can still, of course, get to hydrodynamic, etc. But whether you also, on its way, whether you get also to this kind of classical attractor is not very probable. However, this is a question of principle, and the point is that what you need for that is weak coupling, and that your distribution or your fields, your correlation functions are large, basically. At least 1, 2-point functions, maybe 4-point functions should be very large in order to have more energy than what you would actually expect with a similar thermal state, or the thermal state with a similar hard scale. So this is what I mean by this kind of picture here. It is not exactly that you have this form, but the form is not relevant. The important thing is that your energy density should be dominated at some specific scale, and up to that specific scale, your occupation numbers should be much larger than 1. And if you have this kind of system, then it's, well, I don't really remember. Well, it depends on what kind of topology you have, what kind of vortices maybe you have, because you could have more than just one classical attractor. You could have several non-thermal fixed points, and then it also depends on exactly what kind of initial conditions you prepare it with. But in general, you usually get to a classical attractor if you prepare it in this kind of way. But you only know it for sure when you basically simulate it, or when you compute it. It is expected, but it's not a generic proof. I hope I answered that question.
Johan, I think your microphone is off.
Who's mine?
You know.
No, I think Johan's was.
My understanding was that you mentioned that in ultra-cold atomic gases, this kind of non-thermal fixed point behavior has been observed.
Yes.
So how do you then prepare in these gases the initial condition to reach that?
There are different ways. So you can start with a thermal system, and then basically, and then maybe do a quench. This has been, I think, this is one of the things that have been done. They are different. There are several approaches for that, but it is very tedious to do. I'm afraid I don't have a slide on that. I should have. I have different backup slides, but I don't have a slide on that exactly. That's why it's difficult to show you here. But it is. So it is not a common, it is not a usual state that you use for that you prepared with in ultra cold atoms. And by the way, you cannot do it for fermions. You have to use bosons, otherwise you will not have exceeding occupation numbers over 1.
Yeah, sure.
And this was also why. So these things were predicted already in 2004, 2008, 2015. There were predictions about universality classes of such kind of states, but only in 2018 there were the experiments published, and also in Nature. So it is very non-trivial to get there, and there has been a lot of work put in there. But again, as I told you, so as I tried to say, that basically you have to use some tricks. So usual thermal states, of course, are not enough for that. And I think also 3-dimensional, so basically many things were done here in 3 dimensions. 3-dimensional is also not possible. Basically what they have is effectively 1-dimensional, or basically 1-dimensional with very small extent in 2 and 3 dimensions, and so on. There are different restrictions that, of course, they also work on to extend them, but it is not easy to get.
Thank you.
Okay, do we have any other questions? Okay, if not, then we thank Kirill again.
Once again, thank you very much for your attention, and I was very, very happy to give this talk. Thank you.